Hello, everybody. Good afternoon. Welcome to this seminar of the Astronomy Department of IAG-USP. Thank you for your participation, everyone who is following the seminar via YouTube, via Google Meet, or here present in the auditorium. And today the speaker is Dr. Leonardo dos Santos. Thank you, Leonardo, for accepting the invitation for giving this talk. And Dr. Leonardo got his master's degree from IAG in 2017, and his PhD from the Geneva University, is it right, from in Switzerland in 2021. Yep. And since then, he's a postdoc fellow at the Space Telescope Science Institute in US, where he researches exoplanet atmospheres and is a support astronomer for the Hubble Space Telescope. Today, he will present the talk, Atmospheric Escape and Evolution of Exoplanets. Questions can be made after Leonardo's presentation. And if you are following the seminar via YouTube, you can also write down your questions to Leonardo after the presentation. And for the colleagues who are following the seminar in Google Meet, please turn off your microphones and cameras before the seminar starts. And Leonardo, feel free to start.
All right, thank you. Can you all hear me? All right, so thank you all for coming. I am a postdoctoral fellow at the Space Telescope Science Institute, where I do research on exoplanets, their atmospheres, and I also provide support for the Hubble Space Telescope, more specifically for the STS instrument. If you ever use this, thank you. You are helping me to have a job, so that's good. But today I'll only talk about research. But if you have any questions about Hubble or STS, something like that, you can also come to me for that. So I will talk about very hot exoplanets. And when we say hot, I don't necessarily mean hot like Venus. We know that Venus is pretty hot, something like 800 Kelvin if you go down to the surface of the planet. It's hot enough to melt a Russian probe in something like 10, 15 minutes. But the planets that I'm talking about are even more extreme than that. Take, for example, this planet. It's an ultra-hot Jupiter, and I already apologize for the very non-imaginative names or classifications for these planets. But this ultra-hot Jupiter, called WASP 76b, this planet is so hot and it orbits so close to its host star that it's actually tidally locked to the star. It's a Jupiter-sized planet, as the name implies, and it's tidally locked. So it has a face that is constantly facing the host star. So that's what we call the day side. And on the other side that is facing away from the star is the night side. So what happens is that the day side is so hot that it's actually hot enough to have vaporized iron floating around in the atmosphere. Vaporized iron. But when this material goes to the night side where it's cooler, it actually condenses and it forms clouds made of iron and other materials. And we have observed that. We have observations made from the ground, not from space telescopes, but from the ground that corroborate this hypothesis. So this is a fairly famous result that came out back in 2020. But it has recently been challenged, but that's the overall picture that we have for these ultra-hot Jupiters. But I will actually go back in history a little bit, back to 1996, just 1 year after the discovery of the first exoplanet orbiting solar-type star. This planet is called 51 Pegasi b, and those who are familiar with exoplanets probably have heard about this planet. It was discovered in 1995, and the discovery struck the community because we were not expecting to find a Jupiter-sized planet orbiting so close to its host star within an orbital period of I don't remember on top of my head, but it's something like 2 or 4 days. I don't remember if it's around here. Something like 4 days. So very short orbital periods compared to the Earth that has a 1-year orbital period. So, and it's a Jupiter-sized planet on top of that. So you can imagine how extreme it can be. But back then, back in 1996, just 1 year after that discovery, naturally the community was a bit skeptical about it. So we had this article published on Science, but by then, just 1 year after that, we already knew a handful of these Jupiter-sized planets at very short orbital periods. So we started asking ourselves, how did these planets, these gas giants, end up orbiting so close to a star? Not only that, but how can they retain their gas-rich atmospheres in such a harsh environment? These were the main questions that we were asking at the time, and we're still trying to answer these, by the way. So research is still ongoing. It's more than 20 years now, and research to answer these questions is still ongoing. So fast forward to 2022, and this is more or less the picture of how many planets we have discovered. These are transiting exoplanets, where we have a measurement of the radii on the y-axis, and we also have an estimate of the irradiation incident on the planet in units of Earth flux. By the way, the x-axis is inverted, so more irradiated is to the left, less irradiated is to the right. So don't be too confused by that, but that's the picture that we have now. And this O+ symbol, also I should use my cursor. Yeah, so this O+ symbol is the Earth, so 1, 1. What you may notice just from seeing this plot is that most of these planets, they have irradiation levels that are orders of magnitude stronger than what we have here on Earth. By 4 orders of magnitude, up to 5 orders of magnitude for this extreme ultra-hot Jupiter right here that I know on top of my head. It's called Kelt 9b. So it's a very famous exoplanet in our community. So, yeah?
Well, I'm already interrupting you. So the fact that the cross is at the lower... The fact that the cross is at the lower right corner of this plot, is this a selection effect, or is this the reality of the distribution of exoplanet properties?
Yeah, that's a very good question. So here on the shore, or this very irradiated region of the plot, this is not biased. This is a fairly complete survey that generates this kind of population. But if you go to low irradiation levels where planets have longer orbital periods, then we have a selection effect, because usually these surveys are not sensitive enough for very long orbital periods, something like, I don't know, 10 years orbital periods. These are very difficult to detect. They also have low probability of transiting. They produce very small signals when we do surveys, so they're fairly difficult to detect. Same goes for Earth-sized planets. They're very small, so they produce small signals, difficult to detect. So in this part of the plot, this is going to be more visible when we go to the log space in the y-axis. But small planets, long orbital periods, there's definitely a selection bias in there. But for the short periods and high irradiation planets, we have a pretty complete picture. You're welcome. So yeah, lots of these planets, or most of them, they receive orders of magnitude more irradiation than what the Earth receives from the sun. So it's only natural to ask, well, what happens to the atmospheres of these planets? Don't they just boil off to space? That's something that can intuitively come to your mind. And actually, it goes back to the 19th century with this paper that was submitted in 1845 and only published in 1892, a paper by J.J. Watterson. And this is a very long paper. It discusses many things, and among them, a little bit of a theory of how planets can retain their atmospheres. And I highlighted a sentence in this very long paper where the author concludes that there's a certain regime of temperature where atmospheres will slowly evaporate into space for planets like the Earth. Now, little did this person know, the author know, that more than 100 years later, more than a century later, we would observe this kind of effect not only in the solar system, but actually mostly outside of the solar system in exoplanets. But I'm getting a bit ahead of myself. I want to go back to those hot planets that I mentioned in the beginning a bit. So the way that atmospheres escape to space kind of works like this. This is going to be very hand-wavy, by the way. I'm not a theory person. I'm mostly an observer. So I'm going to hand-wave a lot for my explanations. But what happens is that you have your planet right here that has an atmosphere. Can be made of hydrogen, can be made of many different things. But if the planet has an atmosphere and it has a whole star that emits extreme ultraviolet radiation, when this irradiation hits the planet, it's going to be absorbed by the upper atmosphere. More specifically, for those who are familiar with atmospheres, it's going to be absorbed in the thermosphere. And the atmosphere is going to expand. And depending on how much volatile material the atmosphere has, like hydrogen and helium, and depending on the amount of irradiation arriving at the atmosphere and how much is absorbed, this expansion can become very fast, and it can produce an outflow. And if this outflow is supersonic, or if it exceeds the sound speed, it becomes a process called hydrodynamic escape. I'm just trying to make you familiar with some of the terms that we have because I'm going to mention hydrodynamic escape quite a bit. So just imagine an outflow that becomes supersonic. So these are pretty extreme planets. Here on Earth, we don't have, it would be weird to have a supersonic outflow in our atmosphere, but we don't have that. Our planet is not a hydrodynamic escape. It's another regime. But I'll talk about the Earth a bit later. The reason why we're interested in hydrodynamic escape is because we think that this process is responsible for shaping the picture for demographics of exoplanets. Just imagine census, like the census that we have for our population here in Brazil, for instance. We do make that kind of study for planets as well. Now I'm going back to that plot that I showed in the beginning, and now the y-axis is in log space. And just to complement my answer from before, this is the region where we have low completeness for our surveys. So anything below this triangle that I'm doing right here, it's probably biased. Anyway, I want to draw your attention to the different types of planets that we know. So we have Jovian planets, we have Neptunes, and we have rocky planets or Earth-sized planets. And as I said before, this part of the plot where we have high radiation levels and large planets is fairly complete. We don't know many biases in there. But we still see a lack of planets right here in this region that I'm tracing here. There's also another one that is a bit more difficult to see by eye, but it's statistically significant. There's a lack of planets here as well, where I'm tracing my cursor. So these regions are known as the hot Neptune desert and the radius valley. And there are many other features in the demographics, but I want to draw your attention to these two because these two we think are carved by atmospheric escape. So what happens with these very hot planets is that they have, first of all, if they're Jovian or Neptune sized, they have large envelopes made of hydrogen and helium, so very volatile. And when they are put under harsh environments of high radiation, they start losing their atmospheres at very large rates. They have hydrodynamic escape. So they actually start shrinking. So these planets, they shrink in size, which is why we have a direction of radius evolution towards the bottom of the plot. So these planets shrink and they start drifting towards the lower parts of this plot. So they start depopulating the desert, and they start depopulating the upper edge of the valley and populating the lower edge of the valley. because of hydrodynamic escape. But yet, there are still many unknowns about this process, and these are the types of questions that we're asking right now. For instance, what are the timescales of radius change and of mass loss? What is the efficiency of converting the stellar photons, the high energy photons from the star, into an outflow? And how much does the internal energy of the planet contribute to atmospheric escape as well? So it's not only the star, but also the internal energy residual from formation, how much of that contributes to escape. And we're always asking about magnetic fields and their role in the process. But as you can imagine, it can get very complicated when you put magnetic fields in there. And in order to answer these questions, the most natural way as scientists of answering them is by performing experiments. And the experiments that we do, the most productive one is called transmission spectroscopy. So imagine that many of you have heard of planetary transits or exoplanet transits. So basically, you wait for a planet to transit the star or to pass in front of the star, and you measure the changes in the stellar light before, during, and after the transit. Now, in transmission spectroscopy, you do that instead of just photometry, you do spectroscopy of the transit. So you wait for your planet to pass in front of the star, and you measure that at different wavelengths. If the planet has an atmosphere, different components in the atmosphere are going to absorb at different wavelengths, and you're going to have different shapes for the light curve that you see here in the bottom. So in the bottom, we have these different light curves with different colors corresponding to different wavelengths. So that's what happens. And if the planet has an atmosphere and if it transits, it changes the light curve like that. I'm going to play it again so you can see. Again, just pay attention to the light curves here in the bottom, how their shapes change with wavelengths. So that's the telltale sign of an atmosphere in a transiting exoplanet. So it's kind of like measuring the size of a planet. And depending on how diffuse and how extended the atmosphere is, it's also kind of like measuring the level of transparency of the atmosphere. So that's the gist of it. It can get much more complicated than that, but that's the gist of it. The most famous case of atmospheric escape detected in an exoplanet is that of a planet of a Neptune called GG426b, or Gliese 426b, depending on who you ask. This is the archetypal evaporating Neptune planet. So back in 2015, actually my former PhD supervisor and his team, they observed a transit of GG426b using the Hubble Space Telescope and the STS spectrograph, which I currently provide support for, interestingly. They observed the Lyman alpha line of the host star before, during, and after the planet transit. And what they observed is that the blue wing, or the blue shifted wing of the Lyman alpha, this is the Lyman alpha line, by the way, and it has this shape because, so it was supposed to be kind of like a Gaussian emission line, but because of interstellar medium absorption, the core of the line is absorbed. It's basically, it goes to 0. And we have access to only the wings of the line. So this is why it has this funky shape. It's not a doublet, it's a Gaussian that has absorption in the core. Anyway, here in the blue wing, when the planet well, first of all, before the transit, we have the spectrum in black, which is right here. And the different colors are different phases of the transit. So you see that during the transit, we have an absorption of almost 50% in the spiral of the stellar line. Now, the transit of the planet, the opaque disk of the planet itself, it's less than 1% absorption. So all this additional absorption of about 50% has to come from something else. And the something else is a large hydrogen cloud around the planet. So in this simulation right here, we have the actual planet is just this black dot here that is just a few pixels. And this huge feature, or this huge cloud around it, is made of atomic hydrogen that is fed by atmospheric escape from the planet. And this is a zoom out in the system. And this yellow circle is the host star. It's an M dwarf. And the planet is right here. So you see that the exosphere of the planet, which is this cloud, we call them exospheres. it's actually larger than the whole star, which is pretty impressive, which is why it blocks so much of the stellar light in this particular spectral line. Actually, if you go back to the raw, if you have your computer right there with you and you download the raw data of this observation, you can actually see the signal by eye in the raw data. No reduction, no nothing. Just the counts, the raw counts in the image, and you can see by eye. If you have, I forgot the name of the software that we use to look at FITS images, but if you use that, you can, and you blink the different frames, you're gonna see this absorption by eye, which is pretty impressive. This is the strongest atmospheric signal ever observed for an exoplanet. We have reproduced the same signal using another instrument on HST called COS, or the Cosmic Origins Spectrograph. Ironically, it's not only observing the cosmos and cosmology, but it's also observing exoplanets, which is cool. And here on the right, so first of all, here on the left, you have the time series of the Lyman alpha profile, and you see that the blue wing changes with time. And here on the right, you have a light curve of the blue wing of the Lyman alpha line, and you see that there's this absorption of about 50%. Again, it can only be explained by a large hydrogen cloud around the planet. And simulations show that the mass loss rate of this planet is in the order of 10 to the 9 grams per second, which, for instance, compared to the Earth, the escape rate of the Earth is about, I think, 10 to the 5 grams per second. So this is orders of magnitude more mass loss than the Earth. And we think that this planet is in a state of hydrodynamic escape. Now, when a planet is at this regime of hydrodynamic escape, not only hydrogen escapes, but also other heavier species like iron, carbon, nitrogen, oxygen, magnesium, all kinds of other components. And we have actually observed this in other exoplanets. So this is a collection of the many different metals that have been detected in transiting planets. We have oxygen, atomic oxygen, ionized carbon. We have carbon again, magnesium, and I'm not showing one here, but there's also detection of iron in this planet called WASP-121b. And not only metals, but we have also a collection of many planets where we have also detected escaping hydrogen using the Lyman alpha line that I showed you before. And again, this is a collection of them. Most of them are hot Jupiters, like the ones here in the top left and top middle. These are hot Jupiters. The other ones are probably Neptune-sized planets like GG 3470b, Happy 11b. And this is a very young planet, HD 63433c. I apologize for the names of these planets. They're kind of ridiculous, but it is what it is. I want to draw your attention, though, to K218b, because if you're familiar with exoplanets and you were looking at the astronomical news or just normal news back in 2019, if I'm not mistaken, you would have seen something like this. K218b being portrayed as an Earth-like planet that has water in its atmosphere, just like the Earth. We do have water in our atmosphere, but what happens is that K218b is not Earth-like. It's the size of a, just shrink down Neptune a little bit and you're gonna have a planet the size of K218b. So this is not Earth-like. It's just a mini Neptune with water vapor in its atmosphere and also a lot of hydrogen and helium. So very unlike the Earth. So let's forget those news for now and let's go to the actual science, because back in 2020, we observed this planet, again using Hubble and using STS to detect escaping hydrogen in this planet, and we actually managed to detect something. But it was a bit challenging to interpret the data because I don't know if any of you here is familiar with STS observations in UV, but this is kind of like the raw data looks like. So this streak, this vertical streak, is contamination from the Earth. It's a geocoronal contamination from the Earth. And the stellar signal is this tiny smudge, just like a few photons in an exposure of HST. So I will zoom in this region just so you can see the smudge. So this is the smudge. This is just a few photons here in the horizontal direction. And this streak, as I said, is contamination, so we're not interested in it. But it bothers us, and it's difficult to correct for. But it is possible. And when we analyze the light curve of this planet, or the blue wing Lyman alpha light curve of this planet, we see a decrease, again, a very large decrease on the stellar flux in the blue wing, while the red wing flux remains more or less stable. And this is the telltale signal of a hydrogen cloud that surrounds the planet that we see during the transit. And here in the bottom, we have the outer transit and in-transit Lyman alpha lines of the whole star. But as I said, K218b is a bit different from Earth. It's also a bit different from the hot planets that I talked about before, because K218b receives the same level of radiation that the Earth receives, but it's a mini Neptune-sized planet right here. And the Earth, as I said before, is this O+ symbol. So yeah, it's not a hot planet, but it still has atmospheric escape and is detectable, or at least it's a tentative detection. We need more data to be more secure about that detection. But this indicates to us that even temperate planets can also have escape and can also be detectable, which brings me to Earth-like planets. Now, what I'm showing you here, this is not a simulation. This is actual data, except this circle here. That's the little Earth that I put right there in that central pixel. But this huge blob around us, this is an actual detection. So some people from, it's a group from Japan led by Shingo Kameda. In 2017, they published this result. So what they did, they launched a satellite into the space, and they pointed that satellite to the Earth, and it measured the Lyman alpha luminosity of our own planet. And what you see here is the Earth's exosphere, rich in hydrogen and very extended, scattering Lyman alpha photons from the sun into the detector in that satellite. So this huge feature right here is our little exosphere made of hydrogen, fed by atmospheric escape from our own planet. Now, we're all breathing right here, and there's not a lot of hydrogen or atomic hydrogen or molecular hydrogen around us. But we do have water. So what happens is that the water molecules, when they go up to the upper atmosphere, they photodissociate, and they photodissociate into atomic hydrogen and atomic oxygen. And because hydrogen is very light, it escapes the planet, and it forms this beautiful feature that you see right here, this pale blue smudge. It's not a dot. So yeah, inspired by this observation, we wanted to test if such a feature can be observed in exoplanets, because our exosphere, the Earth's hydrogen-rich exosphere, is actually very unique when compared to other rocky planets in the solar system. So we think that if we can detect this in an exoplanet, it could point out that maybe it's an Earth-like planet. We have a question.
Yeah. So is it my impression or the exosphere is distorted?
It is distorted, yeah.
Solar wind?
It's probably a combination of many things, like solar wind and radiation pressure from the sun.
Mm-hmm.
So it does have this sort of like distortion. And if you're interested in seeing that, you can check this paper by Shingo Kameda, 2017. They described that very well. So yeah, we wanted to see if this kind of feature is detectable in exoplanets. So we published a paper back in 2019 where we did this test. I'm gonna skip all the technical stuff from the paper and just give you the raw or the meaty result that this is not detectable with Hubble. And to be honest, I wasn't really expecting it to be detectable because Earth-like or Earth-sized planets are difficult to study right now. In fact, I don't think we can detect an atmosphere in an Earth-like planet at this point, even with JWST. But in the future, we're going to have the true successor to Hubble that at this moment doesn't have a name, but by then, in 2019, it was named LUVOIR, which stands for Large Ultraviolet Optical Infrared Surveyor. And when I say it's a true successor to Hubble, it's because it has the same spectroscopy capabilities as Hubble, from ultraviolet to infrared, as opposed to JWST, which has only infrared capabilities. We are very excited about this because I forget the name of the report, but there's this report that is made by the astronomical community in the US, the Decadal Survey, yes, thank you. The Decadal Survey that compiles the several white papers from the entire community in the US. They did push forward, or they did push the envelope for LUVOIR, or whatever it's going to be named. I think currently it's not being named LUVOIR. It's currently called the next flagship space mission for NASA or something like that. But whatever. I still call it LUVOIR because it doesn't have a name yet. But it will have a name in the future. So it's planned to be launched in 2000 or in the 2040s, maybe 2050s. And the whole community is very excited about it. The Space Telescope where I work, Space Telescope Science Institute, everyone, maybe not everyone, but there are many people who are gearing up to put this mission forward. And my impression is that NASA is also interested in pushing it forward, so we're very excited about it. And this telescope is going to have two ultraviolet instruments that we could use to study exoplanets. One is LUMOS, which you can imagine as like a STS on steroids. It's basically a successor of STS. And there's also Pollux, which is kind of like a STS, but it has polarimetric capabilities. So if anyone wants to do polarimetry in the UV, look forward to LUVOIR. But this telescope is going to be able to detect Earth-like exospheres, or at least from the test that we did. So what we're looking for, again, these are light curves in the ultraviolet, in the Lyman alpha specifically. What we're looking for is this dip here in the residuals. So if you find this dip in the residual, that's the signal of our Earth-like exosphere in there. So this is a simulation for 10 transits. This is a simulation for 20 transits. And they both look promising with LUVOIR, but not with HST, unfortunately. So we were going to need to wait for the future to find these potentially Earth-like planets. All right, so far I talked mostly about ultraviolet, Lyman alpha, and metals. But there's also another channel that we can use to measure atmospheric escape in exoplanets that does not necessarily need a space telescope. It's the metastable helium line in the infrared around 1 micron. And people who do stellar physics or stellar studies may be familiar with this line. It has only recently become exciting for exoplanets back in just as of 2018 with a paper published by Antonio Kopcic and Hirata, where they discuss how this line or this triplet can remain stable enough and survive long enough in a planet's atmosphere to be detectable during the transit. So the transition that we're looking for is this one right here. It's 23S to 23P, and the line is formed at 10,000 angstrom. So near infrared, we have access for it from the ground, potentially a high resolution. So for instance, if I go back one slide, this is a high resolution observation. From space, you cannot do high resolution unless you're in the UV. But in the infrared, you need to be on the ground to do high resolution. And we're interested in high resolution because we have access to velocities. So we can study atmospheric escape in velocity space, which is pretty nice. Another advantage is that this line does not have interstellar medium absorption, or if it has one, it's very small. So it's all good here. So this technique has become so productive that we have studied many exoplanets using metastable helium observations. And this plot here shows in the x-axis the high energy flux incident in the planet. And this time it's not inverted, so less irradiation to the left, more irradiated to the right. And in the y-axis we have a weird measurement. It's the in-transit absorption per unit scale height. It's basically the amount of absorption that we have during the transit. That's basically it. So we have many detections shown by the crosses, but we also have many non-detections shown by the upper limits and the downwards arrows. And then the reason why we make this plot of high energy flux versus in-transit absorption is because back when we were starting to do these kinds of observations, we were seeing a trend where the more irradiated the planet was, the stronger was the in-transit absorption. But nowadays, and this is a paper that we recently published earlier this year, the picture is much more like all over the place. So we're trying to piece things together right now with this larger sample that we have. But one key piece of information that is tricky to measure, but we need that information to start understanding the role of escape or atmospheric escape in the evolution of planets, is to measure the mass loss of these planets. And it was with that in mind that back in 2021, I started developing a code called PWinds. It's basically a 1D model based on the Parker description of the solar wind that we apply to very hot exoplanets. And we, based on this model, we can try to extract a mass loss rate for the planet. So back in 2021, and I'm going to show you a very quick timeline of how the code was developed, because I think this is interesting. This is my GitHub timeline as of 2021. And I had this intense initial development phase back in the beginning of the year. In March, I was busy writing proposals for HST in cycle 29. But then by May, we started doing some improvements and testing in the code. And we got the first results by June, beginning of the summer, 2021. And we submitted a paper in August. And in September, we started implementing the feedback from the referee, which was pretty useful. And the paper was accepted by the end of the year and published earlier this year. I think it was either January or February. Now, with this kind of model, as I said, it's a very simple 1D model. You can start producing models of how the in-transit absorption looks like for the helium triplet, depending on the phase of the transit. So if the transit is near the limb of the star, we have the yellow curves. And if the transit is near the center of the star, you have the deeper, darker curves. And in red and dashed is the average of the whole transit, which is usually what we measure when we measure a transmission spectrum. And this is just a forward model. But we can also use those models to fit to observations. So what you see here on the left is a transmission spectrum of the helium triplet in the warm Neptune HET P11b. And so the observation is in black. The models that we fit to this observation are shown in red. And finally, after all this, since the beginning of the talk, I can finally talk about mass loss rates, which is the m dot. Is the thing that we are mostly interested in. It's the mass loss rate that controls the evolution of planets. And it hasn't been, we can kind of get measurements of the m dot from Lyman outflow observations, but it's very tricky to do. You need to do 3D simulations. It can get super complicated and expensive. But with the metastable helium line, we can do that using simpler models. And we finally have an m dot estimate. And based on this estimate for the mass loss rate, you can finally start answering those questions that I posed in the beginning of the talk, like timescales of mass loss, radius change, what's the efficiency of converting the stellar photons into an outflow, and we can start finally having fun with this. And earlier this year, some colleagues of mine from Caltech, they led this paper where we measure the mass loss rate for a sample of planets using the metastable helium line. And here on the y-axis, you have a measurement of the mass loss rates, the m dot multiplied by a k factor that accounts for Roche lobe effects. And we plot that against the high energy radiation level at the planet divided by the density. And we have this kind of picture here. Now, the reason why we want to make this kind of plot is because, or this kind of relationship, is because theory predicts that the mass loss rate should be proportional to the amount of high energy radiation that the planet receives divided by the density. And we are finally starting to have a picture for that. But this is only the beginning. We want to expand this to many more exoplanets that have been observed with the metastable helium line. And that's the future vision for my projects, basically to start exploring these evaporating planets in a more of a demographic sense. Instead of just observing one and just studying that one, I want to do that for many planets, start drawing conclusions from a populational level study. All right, so I'm almost at the end of my talk, but I want to show you a result that I'm fairly excited about. So our community is very excited about the metastable helium line because we can observe it from the ground and we can extract a lot of information from these observations. But as it turns out, we have this huge, very expensive space telescope that was launched at the end of last year that can actually observe the metastable helium line in near infrared at lower resolution because it's a space telescope, but it can detect much fainter signals. So the result that I'm going to show you right now is preliminary. It has just been submitted this morning, so I ask that you please don't share it on Twitter or anything. But we did detect metastable helium line for I believe it's a hot Jupiter. I don't remember now on top of my head. So this is the transmission spectrum of the planet. So as you can see, it's much lower resolution, but the signal is very shallow. It's I don't know how many ppm this is, but it's very shallow. So you need a very precise instrument to measure this kind of signal. And here on the right, you have the light curve of the helium feature shown in blue, and in orange, it's the other wavelength channels where you don't have a signal. And you have a slightly deeper signal in the helium channel than in the other pixels. So that's the signal of helium escaping this planet, which is pretty cool. So yeah, we can do that from space as well. I'm not sure if you want to write a whole proposal with JWST just to observe the helium line, because it has access to many other lines where you can observe many other features in exoplanets like water, carbon dioxide, and ammonia, methane, many other things. But if you want to include atmospheric escape in a proposal, you can do that. So it's kind of like a byproduct of expensive JWST observations, which is good. All right, so I'm gonna finish very soon, and I will leave you with some take-home points from this talk. First of all, hot Jupiters and Neptune-sized planets, they are a laboratory to study atmospheric escape and evolution outside of the solar system. Ultraviolet observations that I discussed ad nauseum in the beginning of the talk, they are scarce, they're difficult to get, it's difficult to get time with the HST. And when you get, sometimes you have failed observations, but it's because it's an aging instrument. So these observations are very scarce, but they're very valuable. For instance, Lyman alpha probably probes different or lower ionization conditions for a planetary exosphere. So you can study planets that have much lower radiation levels, like K218b, compared to very hot planets. Helium observations that can be done from the ground, they have become very popular, very productive, and everyone is excited about it, at least in the community. But they tend to be biased towards K-type stars or K-type hosts and hot planets and hot gas giant planets. And finally, and this is something that I've been pushing as of late, we need to analyze the sample of evaporating planets with a common framework, which is the whole point of developing the P-WINS code that I discussed very briefly. We want to apply that to a demographic sample of exoplanets, start drawing conclusions from that, and finally try to piece together how planets evolve in the face of the harsh environments that they inhabit. All right, with that, I will finish my talk right here, and I'm open to more questions if you have any. Thank you very much.
Thank you, Leonardo, for the very clear and interesting talk. Now it's time for questions. So, Siriaco, the first one.
Well, first of all, thank you for this very nice talk. perhaps it's a naive question, but to measure mass loss, or can you measure mass loss measuring kinematics of these gas clouds? And if so, what's the crucial observable that you need? Do you need high spectral resolution and therefore a very sensitive telescope in order to, to get signal on very small velocity channels? Can you comment on that?
Yeah, this is a very good question. Actually, the first estimates of mass loss for these transiting planets were done using kinematics from the escaping material. So I may need to go back several slides, but if you go to the, where is it? Yeah, if you go to the Lyman alpha line that I discussed in the beginning, basically we have access to a fairly high resolution. I think this, in this configuration, was a resolution of 12,000 spectral resolving power. So the R 12,000 approximately. So it's medium resolution spectroscopy, but we still have access to a fairly good resolution of velocities from, I think a resolution element here was something like, I don't know, 10 kilometers per second or so, or 20 kilometers per second. So medium resolution, but you can still see that the material that is escaping the planet has very high velocities of about 100 kilometers per second. So just if you apply a model like the one that I showed later, the P-winds model, that's just 1D Parker wind model. If you apply that kind of model to try to explain Lyman alpha observations of GG46b, it's not going to work. Because this material that we observe at such high velocities, 100 kilometers per second, it's so far from the planet. So these velocities of about 100 per second, they're in this like blue-ish part of the cloud. So you need 3D simulations to try to model this part of the hydrogen cloud, because it's not, you don't have a spherical symmetry here anymore. Maybe it's cylindrical. It's actually a model with a paper that came out very recently where they do apply a cylindrical simple model to try to understand the tail of transiting planets in Lyman alpha. And from that, maybe you can get reasonable estimate for the mass loss rate, but you're going to get ballpark order of magnitude estimate. So it's not, you're not going to get something as precise as you can get from a Parker wind 1D model that models the like the closer, like the spherically symmetric part of the exosphere. So it is possible to do, to get mass loss rate from the kinematics of the escaping material. And it's usually done for the Lyman alpha line. If you go to the helium line, we need to go forward several slides, but if you go to the helium line, our instruments are currently not sensitive enough to study the tail of escaping helium from these planets. Maybe with JWST we can get some precision for that, but for the helium line it can get very
less
tricky.
resolution probably. Spectral
It's sensitivity of the detector, because the tail signal gets very faint for the helium. For the Lyman alpha it gets very large, but for helium it's a very tiny signal.
Okay, thank
So
you.
maybe with JWST.
If I can add a very quick question, what's causing this particular shape of the cloud? Is it orbit? Is it solar wind? It's very
Yeah, it's another very good question. That is kind of a point of very heated discussion in the community right now. People who do simulations of atmospheric escape. As I said, I'm an observer, so I may not have the best picture of how things are, but we think it's a combination of radiation pressure of the stellar radiation arriving at the exosphere of the planet. There's also the orbit. It's kind of like a comet in the solar system. It's kind of like a comet. We call this a comet-shaped. In fact, I think the title of this paper at NIH 2015, I think the title is A Comet-Shaped Exosphere on the Planet, something like that. But it involves radiation pressure, involves stellar winds. There are actually really nice papers that came out recently discussing the role of stellar wind in shaping these exospheres around hot planets. I don't have a slide here, but there is a paper that came out earlier this year that used hydrodynamic simulations to try to understand the role of stellar wind in shaping these exospheres, which is pretty cool. Magnetic fields may play a role as well, particularly for, maybe not for neutral species like hydrogen, but for ionized species like the metals that I showed here, magnetic fields may play a role in shaping these light curves that we're seeing right here. In fact, this paper by Benjafelt and collaborators, 2022, they do discuss a very extensive model that can be used to try to understand the role of magnetic fields in shaping this light curve. So you can take a look at that if you're interested in the magnetic effects. Anyway, there's lots of things that do play a role in here. So it can get very complicated, which is why Lyman alpha is difficult to interpret.
Thank you.
More questions? Thank you. Thank you.
I'm curious about the mechanisms that lead to a shrinkage of the radius of a planet.
Yeah.
Can you comment about that?
Yes, or let me go back to, this slide.
Because the atmospheric evaporation is very intuitive, but radius shrinkage is a bit strange for me.
I can understand that. So just imagine a planet that loses a lot of its atmosphere. And because the atmosphere is mostly made of hydrogen, and it's basically losing that, it's going to shrink because it's losing the atmosphere.
Is in this sense, not in the sense that the solid part of the planet is shrinking.
Yeah, it's the atmosphere.
Wow, okay, thank you.
Yeah, no, it's not the solid part, which is why I only talked about the gas giants. Well, I did mention all right, let me find my cursor here. I mostly talked about gas giant planets like Jovian or Neptune's. But the radius valley does involve planets that have a rocky or a solid core. But what happens is that above the radius valley, these rocky cores, they have an envelope of hydrogen and helium. Just like the Earth in the beginning, when the Earth had just formed, it did have an envelope of hydrogen and helium. It's just that we lost it very quickly. Same for Mars. So at some point in their lives, pretty much every planet has, even if it's very tiny, it has an envelope of hydrogen and helium. It's just that they lose it very quickly. So what happens is that these planets above the edge of the radius valley, we think that they have this envelope of hydrogen and helium, and because of atmospheric escape, they lose this envelope. So they shrink in size and they become bare rock planets, or planets with a secondary atmosphere that is not made of hydrogen and helium. It's made of, I don't know, carbon dioxide, nitrogen, and other species, but it's a more contracted atmosphere, just like the Earth. And another interesting aspect involved with the radius valley is that here in the solar system, so here in the solar system, we only have rocky Earth-sized planets or gas giants. So it's kind of like a binary understanding that we have of rocky planets and gas giants. But when we look at exoplanets, we seem to have a continuum. So we also have what we call mini Neptunes, which are these, you can imagine them as miniaturized versions of Neptunes. And these planets, because we don't have examples of those in the solar system, a lot of the open questions that we have right now in the field is trying to understand what's the nature of these planets. Are they miniaturized versions of Neptune? Are they super Earths with a very large envelope of hydrogen and helium? What are their cores made of? Do they have like an Earth embedded by an envelope? Or we're still trying to understand what's happening with these planets. And this is definitely an area of very active research right now. It's trying to understand what happens here for these sub-Neptune planets just above the radius valley or surrounding the radius valley.
Okay, thank you.
So, one more question.
So how much is the effect from the internal heat from the home planet for the evaporation of the atmosphere?
another very good question. You are all doing very, very good today, because these are all very good questions. This is another excellent question, also very open at the moment. The role of the internal energy to the evaporation of the planets is currently being discussed by many people in the community. We think the thing is, it's difficult to, when you observe an evaporating planet or atmospheric escape on a planet, it's difficult to disentangle it from what we call photoevaporation, which is the one driven by the stellar radiation. Yeah. So this is photoevaporation. The evaporation or escape in the planet is driven by the radiation coming from the star. And trying to piece that, or trying to disentangle that from evaporation caused by the internal energy of the planet is very difficult to do if you have only the observation. So the effort being done right now is coming from the theory side, trying to understand how much the internal energy can contribute to evaporation. What it seems to happen right now is that for very young planets, and I might not say young, a young planet to me is anything up to 100 mega years. In this phase of the planet evolution, we think that we can disentangle photoevaporation from core-powered mass loss. That's the formal name of the theory, is core-powered mass loss. We think we can disentangle them, and we need to observe more of these very young or adolescent planets that are younger than 100 mega years. We think that it's with these observations that we're going to be able to disentangle them. The challenge is observing young exoplanets gets very, very tricky, and you probably know that better than I do, that stellar activity is very prevalent in young stars, and it starts affecting spectroscopy, the spectroscopy that we want to do to detect planetary atmospheres. So disentangling planetary signal from stellar signal from hydrodynamic or photoevaporation from core-powered mass loss, everything gets really, really difficult. But there are a few key young planets that I think we could observe and try to answer this question that you posed. So the key is to observe more young exoplanets and try to understand how to remove stellar activity contamination from the signals that we're looking for.
Okay.
I know that I did not answer your question, but it's because it's an open question right now.
Obrigado.
So let's finish thanking Leonardo again for his talk.
Thank you.
So thank you very much, Leonardo, for this nice talk and for sharing your research and even your very new results. And now we will finish the transmission, and we will invite the presents to the coffee break in the outside of the auditorium.
Thank you.